Data center fire protection is built on a specific core objective: achieving fast fire control with acceptable collateral damage, ensuring the facility can safely restore operations. Meeting this requirement means moving away from a one-size-fits-all approach to a room-by-room architectural strategy. The protection map shows how environments dictate the baseline suppression system. Wet pipe systems protect conditioned support and mechanical spaces. Because water remains in the piping, they provide the fastest discharge when a sprinkler activates. For exposed areas like loading docks, dry pipe systems use pneumatic pressure to prevent freezing. In water-sensitive IT environments, preaction systems remain dry, requiring a specific detection signal to admit water. These pipe cross-sections define the three architectural states: constant water pressure, pneumatic supervisory pressure, and the normally dry detection-released state. The selection of the system determines the latency of water delivery, which directly establishes the risk profile of the facility. Modern fire suppression requires piping, pneumatic nitrogen, and digital logic to function as a seamless entity. This integrated system relies on three interdependent gears. The mechanical piping layout controls a fire before it spreads. The supervisory nitrogen regulation prevents internal pipe corrosion. The digital gear handles detection logic and security operations center status supervision. This mechatronic triad is mapped physically across the data center floor plan to create distinct protection zones. A floor-zoned preaction architecture's boundary is the preaction valve, separating water and gas zones. Upstream is the red zone, continuously pressurized with fire water up to the valve. Downstream is the green zone, containing supervised nitrogen gas until a digital signal opens the valve. This digital interface maintains a strict separation between command and monitoring. While the building management system tracks read-only event logs, only the UL-listed fire alarm equipment is permitted to execute life safety command logic. Unifying mechanical supply with digital logic establishes a fault-tolerant boundary that prevents accidental discharge while ensuring system readiness. Preaction systems are often misunderstood as a replacement for water-based suppression. In reality, they are not clean agents. In a real fire, heat is always required to physically shatter the glass bulb and open the sprinkler head. Preaction logic doesn't stop this operation. The preaction valve acts as a physical logic gate, requiring verification before it allows water to enter the piping network above the IT equipment. A single interlock configuration functions as a Boolean OR gate. This configuration provides earlier water availability in the piping, but it carries a significant trade-off. A single false smoke detection will fill the downstream piping with water. A double interlock configuration operates as an AND gate. It requires both a smoke detection signal and the physical opening of a sprinkler head, detected through pneumatic pressure loss, before water is admitted. While double interlock protects against accidental discharge, it introduces hydraulic delivery delays that must be managed through precise engineering. To maintain fire control, every step of the release sequence, from detection to discharge, must be timed and verified. The sequence begins at T0 when smoke is detected, followed by the releasing panel confirming the criteria. Adding unapproved release delays during these initial phases compromises the system's effectiveness. Once the criteria are met, the solenoid operates, physically opening the path for the preaction valve to trip. As nitrogen vents and the clapper opens, pressurized water enters the piping. Finally, the heat of the fire opens the sprinkler element to begin discharge. This mechanical interplay is visible in the intricate design of the preaction valve trim. When the solenoid release valve opens, the main clapper drops, transforming the dry pneumatic zone into a pressurized wet zone. Beyond the valve operation, the water must also have a clear physical path to reach the hazard. NFPA 13 defines strict spatial geometry rules to ensure that water discharge is not blocked by fit-out obstructions. A minimum 18-inch clearance is required between the sprinkler deflector and the top of any server cabinets or containment structures. Because of these clearances, every fit-out change, such as adding new cable trays, requires a full reevaluation of the hydraulic design. Even a perfect mechatronic sequence cannot suppress a fire if physical obstructions prevent the water from reaching the heat source. Complex suppression systems require continuous diagnostics to identify and mitigate failure modes before they compromise the facility. This failure mode analysis maps specific risks to their consequences and the necessary safeguards. A closed control valve renders the system unavailable. This risk is managed through supervised tamper switches and formal lockout-tagout procedures. Loss of nitrogen pressure can lead to valve instability. This is prevented by supervising pressure trends and monitoring the nitrogen generator's run cycles. We must also manage inherent physical vulnerabilities of dry piping, specifically the accumulation of trapped water. Low-point management is required to collect and drain the condensate that naturally forms within pre-action branches. By utilizing a water presence sensor in the drain pot, the system provides a maintenance trouble signal to the facility team without triggering a false fire alarm. Every safeguard must be proven through rigorous testing and commissioning. Trip and water flow testing provide the timing, hydraulic, and signal data required to verify system readiness. The system must meet strict hydraulic thresholds, typically requiring water delivery to the remote test connection in 30 seconds or less. Verification requires using a single synchronized clock to confirm that signals are received at the fire panel, the BMS, and the SOC simultaneously. Maintaining this level of readiness over the system's lifecycle requires strict governance during maintenance and repairs. The impairment governance loop prohibits undocumented closures and bypassed panels without a fire watch. No system is returned to normal status without a witnessed retest. The standard of a data center suppression system is verifiable readiness. A system is only valid if precisely engineered, rigorously testable, and safely restorable.